We're ready to talk about section 2.4. 2.4 is all about constant functions. And just to give a little bit of background here, for a constant function, here's a fact that we know from Calc 1. So here's a fact that we know from Calc 1. We know that if f is a function that's 0 for all values x in I, so if we have some interval over which the derivative of a function is 0, that means that the function f is going to be constant. And the proof here is the mean value theorem. Okay, so the proof here is going to be the mean value theorem. If you want to see that in action, what that means is that pick two values, say x and y in I. Of course, I mean two different values. Then we know that in between x and y, there exists some value. Let's call it what should we call it? I don't want to use C. Let's call it, so then there exists, let's call it a t between x and y, where we have that f of x minus f of y equals f prime of t times x minus y. But if f prime of t is equal to 0, this tells you that f of x equals f of y. And since this is true for any values of x and y in the interval, that tells you that f is constant. It's just whatever that value is, that's the same value no matter what value you plug in from the interval. And so that's a Calc 1 proof. Okay, so this is really a Calc 1 fact. Now, this fact is still going to be true in complex numbers, but the difficulty is that there's no analog of the mean value theorem, at least not a perfect analog right now of the mean value theorem. So if we have this, we're going to have to have a little alternative proof here. So let's call this a proposition. The same statement's going to be true, but we have to word this a little bit carefully. Let G be what the book calls a region. And what a region is it's an open, connected set in the complex plane. So to be a region just means that you're open and connected. So let G be a region. If f prime of z is equal to 0 on G, then it turns out that f of z is a constant on G. Okay, so this is the analog of the statement that if you have a derivative that's equal to 0, then you know that that function must be a constant on that set G. One thing I want to just think about for a second, first of all, we need open sets to talk about differentiability, because whenever we talk about differentiability, we're talking about a limit, so therefore we have to have, we're thinking about accumulation points there. And so if we stick to an open set, then everything is nice and all the points are accumulation points. What I want to do is I want to think about, though, why do we need it to be connected? Well, the reason is that, and actually something similar can happen in Calc 1. If you were to have two regions, so say you have G1 and G2. And let's say that we know that f prime of z is 0 on G1 and on G2. That does not tell you that f is a constant, because what could happen is that you could have something like, so connectedness is important. So it turns out that you could have something like f of z is something like, I don't know, 1 for all the values in G1 and 4 for all the values in G2. And therefore the derivative is always going to be 0 because we have a constant function on each piece, but it's not a constant function overall, because here you have that the function has the outputs that are one value over here and a different value over there. So that's not a constant function. So this connectedness piece is super important. So what I want to do is let's walk through the proof. And what I want to do is let's pick two values, x and y and g. And then we want to show, that f of x equals f of y. And because the points that we picked, x and y, because they're arbitrary, this is enough to show that the function is constant. Because if f of x equals f of y, then we're done. And actually, I shouldn't pick x and y. This just occurred to me. I should pick, since we're talking about complex numbers, let's pick z1 and z2. Okay, so x and y was just a bad choice of names because we're talking specifically about complex numbers. Okay, so let's let gamma be a path, and gamma is specifically going to be a path joining z1 to z2. How do we know that we can always find such a path between z1 and z2? Think about that for just a second. So how do we know that we can always find a path from z1 to z2? Connectedness, right? Since the region's connected, that means that between any 2 points we can draw a path. By the chain rule, we have the following. So by the chain rule, we have the f of gamma of t. If we differentiate this with respect to t, so if we have the derivative with respect to t, that's going to be f prime. So just by the chain rule, that's f prime of gamma of t times gamma prime. Okay, so we're going to have f prime of gamma of t times gamma of t. Okay, and that's going to be 0, since by our assumption, f prime of whatever we want is 0 for all z in G, right? So gamma of t is just going to be some other point. So gamma of t is just some curve joining z1 to z2. That path is going to be, it's going to stay in G. And so that means at any point along that path, the derivative there will be 0, because that's our assumption. So that's by the chain rule. Okay, and then what does that mean? Well, that means that if f is equal to u plus iv, then let's think about what that means. The derivative of f with respect to t, f of gamma of t would be, let's see. So what we're looking at is the derivative of u of gamma of t plus I times, I did this slightly out of order here, but the derivative of f of gamma is equal to the derivative of u of gamma with respect to t plus I times the derivative of v of gamma with respect to t. And we know that this is going to be equal to 0, right? So we know that this is going to be equal to 0. And so what this tells you, the reason why we know it's 0 is that we just said that this was 0 for the derivative of f of gamma of t, right? We said that that was 0. And this is some complex number 0 plus 0i. And in particular, what that means is that these two pieces are going to be 0, and that's going to be important. So therefore, the derivative of u of gamma of t is going to be equal to 0. And likewise, for the derivative of v of gamma of t, that'll be 0. Okay, for all points on that path. And from calculus, we know that since these are actually just functions of one variable, so this implies that u is a constant. Say u is equal to a. And likewise, v is also a function of one variable. So v is a constant. Say v is equal to b. Thus, our function that we have is also a constant, right? F of x plus y is a plus ib. So therefore, that's also a constant function. Okay, and there we go. That's the proof. So it turns out that even in the complex, even when we're talking about complex derivatives, if we have a function whose derivative is 0, as long as we're talking about an open connected region. If we have a function whose derivative is 0, then that function must be a constant function.